So, hello, am I audible? Okay, so let's continue with our limits and sequences. So last class I proved Cauchy's, Cauchy's criteria and its equivalence with the normal convergence of a sequence. So sequence is Cauchy if and only it's convergent. Right. So today let's start with some basic problems. Finding limits of series and sequence. So suppose xn is a sequence defined by x naught is 0 and xn plus 1 is recursively defined as xn plus 1 equals to square root of 4 plus thrice xn. Show that it's convergent and find its limit. So show that xn goes to some L and also find what is L. So how to go about solving this one? So our basic roadmap will be using MCT for now, monotone convergence theorem. This was, I guess, the first theorem that I mentioned last class, which is you have to first show a sequence is monotonically increasing or decreasing, and then if it's increasing, you have to show it has it admits a upper bound, and if it's decreasing, then it admits a lower bound. If you're able to show that, then the sequence is convergent using this theorem, and the limits are the supremum and infimum respectively. So if you try to compute x1, it's 4 plus thrice 0, which is 2. So x2 is 4 plus thrice 2, which is 6 plus 4 root 10, which is around, is greater than 3. Then x3 is so if you assume it's 3, so then this is actually square root of 30, which is less than 4. But it's certainly greater than root 10, right? So you can see this kind of increasing pattern. x0 was smaller than x1, which in turn was smaller than x2, and which in turn was smaller than x3. So from that we can infer might be the sequence is continuous, strictly increasing. So let's now try to show it's strictly increasing using induction. To show xn less than xn plus 1 for all n. Okay, to do that, so let's assume although it's already true that x0 is smaller than x1, right? So the base case holds. If xn is smaller than, so hypothesis xi is smaller than xi plus 1 for all I inside it starts from 0. So now the inductive steps. So now what is x? So this will run from the plane n plus n minus 1. So n plus 1 is square root of 4 plus 3 root thrice xn. Okay, let's first see what I get after differentiating it. Suppose this is fx. So if I differentiate fx, we have this is a redundant bound. Anyways. Okay, so how to show it's increasing? So we know xn minus 1 is less than xn. So xn minus 1 is 4 plus that. Right, so it was actually pretty easy. So you just need to multiply 3 and add 4 and take square root on both sides. That side will become xn and the item side will be xn plus 1. Okay, so the first step is done. So xn is strictly increasing. Now we need to find a suitable upper bound. From our previous experimentation, we found it's kind of getting stuck at 4. So let's see if 4 is the upper bound of xn. the sequence xn. Now check whether 4 is a upper bound for xn. So we can again fall back to induction for that. So let's assume we can see x0, I mean a0 is 0, so it's less than 4. And let's assume xn, I mean xi is less than 4 for all I inside 0, 1 to n. Therefore xn plus 1 is square root of 4 plus 3xn. So xn less than 4, that implies 4 plus 3xn, square root of that, less than 4, square root of 4 plus 3 times 4, which is 16, so it's less than 4. So that implies xn plus 1 is less than 4. So second claim also achieved. Now we have now xn increasing and xn bounded by 4. Therefore, by monotone convergence theorem, xn converges to some L. So xn is convergent. Now we need to find the supremum. So only thing left is to find the supremum. What is the supremum? The supremum is the smallest upper bound. So let L be the supremum. Therefore, like what will happen at the supremum? Xn will be equal to L, and xn plus 1 will also be equal to L. Like everything will be equal to L. So L is the limiting constant, right? So if we substitute xn equals to L in the recursion, so we get a super quadratic like this. Can be factorized as minus 3 and L plus 1. So L is either 3 or L is equals to minus 1. Just, no, sorry. This is minus 4. So L is either 4 or minus 1. So obviously the limit can't be minus 1 since it's a square root, so it's always positive. So this is extraneous. Therefore, 4 is the limit and the supremum. And we are done. So any doubts, concerns you can raise, or else we're moving on to the next one. Okay, let's try this one. It says so A0 is greater than 0. A1 is equal to 1. So we have a sequence AN with the first two terms positive, A0 and A1. And AN is recursively defined as AN minus 1 plus AN minus 2. So find the limit. Yeah. What is limit n tends to infinity AN? So for this one, again we have to show for monotone increasing first and then boundedness. So very similar kind of problem. So okay, let's try it out then. So AN if we start with A2, so it's A1 plus A0 greater than A1, right? And what is AN minus N plus 1 minus AN? So we are assuming A0 and A1 are in between 0 and 1. So AN plus 1 is AN plus square root of AN minus 1, and AN is A square root of AN minus 1 minus square root of AN minus 2. So we have square root of AN minus 1 term common, and AN minus so we can rearrange it as follows. Right. No, this isn't correct. Yeah, so it's just plus before. So from induction, now we know that if we have assumed AI is greater than AI minus 1 for all I inside 0 to n minus 1, then using the strong form of induction, we can see this is positive and this is positive. Hence, this has to be positive. So n plus 1 is greater than an. So n is increasing, we can show using induction. Next, we have to find a bound. Let's try out some few of the starting. Okay, we can't try them out. Let's assume n is less than 4 for all n inside some 0, 1, 2 up to n minus 1 or n. So an plus 1 is square root of an plus square root of an minus 1. So we know this is less than or equal to, the first one is 2, the second one is also 2, so less than or equals to 4. So it's also straightforward that an plus 1 is less than 4, therefore an is less than 4 for all n. So similarly, an increasing and an is bounded by 4, so by MCT, an converges to some limit L. And now we again use L equals to square root of L plus square root of L. That implies L squared equals 4L. So assuming L not 0, L is equals to 4. So the first two problems we saw today are almost exactly similar. Yeah, I mean the techniques are pretty identical. Right? Now let's move on to solving limits from some properties of limits instead of the direct definition. So limits using properties. So the four properties that we have seen are xn, suppose xn goes to x and yn goes to y, then so suppose then the following holds. Number 1, limit xn plus minus yn is limit xn plus minus limit yn. Number 2, limit n tends to infinity. X and yn is x times y, and xn by yn is x by y. If not only if and only just if if y not equals to 0. Y by y in the limit. And the last one is if limit xn less than, if xn less than or equals to yn, limit xn less than or equals to yn, limit yn. So using these four properties, let's see what we can solve. So problem number 3. Xn is 3n squared 5n plus 4 by 2 plus n squared. So find the limit. Actually, this is pretty easy if you just divide by n squared, but now we will follow only the properties, so we can't use that. So you can break it down into limit of the denominator and limit of the numerator. So now what is limit of n squared as n tends to infinity? So we know some of our items from 1 to n. N squared is n into n plus 1 into n plus 1 by 6, right? From our previous sequences and series knowledge. So now if we take limit, okay, well, you don't need this also. So to find the limit of n squared, first we can't do this, sorry. So first, since limit of, n squared is not, so you see the properties only hold when xn actually converges to x and y actually converges to y. But here n squared doesn't converge to anything, it's divergent, so is n. We can't we can't distribute the limit as of now. First divide by n squared on numerator denominator. So 3 plus 5 by n plus 4 by n squared, 2 by n squared plus 1. Right. Now we can distribute the limits. So 3 plus 5 times limit 1 by n is 4 times limit 1 by n squared plus 2 times limit 1 by n squared plus 1. Now limit 1 by n is so you can see it's obviously 0. If you want to show it from the basic principles, 1 by n minus 0 is, so you can take n equals to, capital N equals to 1 by epsilon. It's less than epsilon for all n greater than capital N epsilon equals to 1 by epsilon or epsilon greater than 0. Similarly, limit 1 by n squared is also 0. You can take n equals to square root of epsilon. Substituting these, in 1 we get limit n tends to infinity xn equals 3 plus 0 plus 0 by 0 plus 1. So it's 3. So the limit is 3. So all those are rational polynomial forms. I guess you will be able to handle those. Now let's move to something a bit more challenging. Okay, this one. find a limit cube root of n squared minus n cube plus n. Okay, so for this one, xn is so basically there is 1 in the denominator now. So what should be the power of n with which we should divide? If you divide by n, you can't divide by n since in the denominator we'll get a 0 otherwise. So if we use the formula a cube plus b cube equals a plus b times a squared minus ab plus b squared, then we will be able to write a plus b as a cube plus b cube over a squared minus ab plus b squared. So let's plug a equals cube root of n squared minus n cube and b equals to n. Therefore, our xn, so xn equals to cube root of n squared minus n cube plus a plus b, so b is n, is equal to a cube plus b cube. A cube is n squared minus n cube plus b cube is n cube, so n cube is cancelled over a squared is n squared minus n cube power 2 by 3 minus ab, so n times cube root of n squared minus n cube, lastly n squared. So this is our new xn. Now we can separate out limits after dividing by n squared. So limit n tends to infinity xn equals 1, so we are dividing by n squared. So n squared times 2 by 3 is 4 by 3. So it's 1 by n minus 1 minus So inside cube root it should be so 1 n cancel, it should be in power 3, so 1 by n minus 1 power 1 by 3 plus 1. So now we can separate the limits. This is the 1, this is also 1, this is also 1. So it's 1 by 3. So the limit is 1 by 3 also. I hope this was clear. No one having doubts? So so we have till now seen two theorems, monotone convergence theorem and Bolzano Weirstrass theorem. That just says we have for any sequence that is bounded, we have a monotone increasing subsequence, so it's convergent. Great. Okay, let's see. So this term is called linearity and monotonicity of convergence of real sequence. So it says if we have if En and Bn are two convergent sequences, of real numbers, okay, so they are reals, real and convergent, then all the sequences of the form, then all sequences of the form, their linear combination, that is from alpha times An plus beta times Bn, is also convergent. If nothing, this alpha beta has to be real. And moreover, that limit is actually also linear. So limit alpha n plus b beta bn is equal to alpha times limit of an plus beta times limit of bn. Actually, we have already used this property up there when distributing the limits in the numerator denominator. So it's nothing new. So I won't go into the proof now. This book is actually pretty concise, so let me check another book. Mm. Okay, let's see some examples where the limits do not exist. Question 5. So we have a sequence xn equals to sine 1 over x minus 1. So is xn convergent? I will give you a few minutes to think about it and draw a few graphs, see if you think it's convergent or it's divergent. Try to use the basic definition. Okay, so did you have any guess why, like, what the limit can be or whether or not the limit exists? This is I could draw the graph. So it's shifted to so at x equals to 1, this is infinity. So for very large values of x, sine of 1 by x minus 1 is actually a very small number. And for something closer to, if you look at the sequence 1 by pi n, you will have a squished up, like a horizontally squished out sine curve. Something like this. So at x equals to 1, this will have like infinite order fluctuations between 1 and minus 1. It will be very large, very quickly. And as you go away towards infinity from 1, it will almost be equal to 0, and so sine 0 is 0. So it will almost merge with the x-axis. Oh. Sorry, actually, I didn't mention the limits. So we have to find x tends to 1 sine 1 by x minus 1. So this is essentially same as finding n tends to infinity sine 1 by n. So for this, you take any two sequences that have the same limit 1, and so you have to find two sequences xn and xn bar, or let's call it yn. Let xn be 1 plus 1 by pi n, and yn be 1 plus 2 by 4n plus 1 pi. You will get to see why this particular choice of xn and yn actually helps. So first observe that they all tend to 1. And then if you take sine over them, so sine of 1 by xn minus 1, this is sine of 1 by, so 1 plus 1 by n pi minus 1, so it's n pi. Okay, let me write it once. The sine of n pi is 0. It's always 0, so the limit has to be 0, right? Therefore, limit n tends to infinity. Sine of xn, f of xn is equals to 0, where f is sine. Again, sine of 1 by yn minus 1 is sine of 4n plus 1 by 2 pi. So at 4n plus 1 by 2 pi, it's It's 1, right? The maximum value at 90 degrees. It's 1 for all n integers. So the limit n tends to infinity for yn is 1. From 1 and 2, this was 1, this was 2, but can we import? So we can see it's initially Fn was essentially the sequence, right? So what did I call the sequence? Oh, I call the sequence xn, and I then assumed xn to be some other sequence. So let's call the initial sequence something else. An, suppose. So An is basically Fn, right? So both f of xn and f of yn are subsequences of An, because they are only jumping at particular periodic intervals. I mean, all of them are already inside An, right? So Fn already contains all of f of xn and all of f of yn. So we have taken two subsequences and it's shown that they actually converge to two different limits. So two subsequence converge to two different limits, and the sequence is bounded. So from Bolzano Weirstrass theorem, we know if a sequence is bounded, then it's convergent if and only if it's every subsequence is also is convergent to the same limit, right? Mm-hmm. So every subsequence, which we have here got two subsequences, f of xn and f of yn, which are convergent but not to the same limit. So by the corollary of Bolzano Weirstrass theorem, An is divergent. Right, so this is one of the ways of showing limit n tends to infinity. X tends to 1, sine 1 by x minus 1 does not exist, right? Doesn't exist. Similarly, can you show this one? Limit x tends to 0, 2 power 1 by x. Does the limit exist or is it divergent? It fluctuates like the previous one. So as x tends to 0, 1 by x actually blows up to infinity, right? And as so this is basically a hyperpolar. So if we take the exponent of 2, 1 by x to the power 2 to the power 1 by x, then obviously this will also blow up pretty fast. And there shouldn't be any, because this is not even bounded, so there is no question. It should be enough to show this is unbounded. So enough to show xn is unbounded. So how do you show something is unbounded? We assume we use a proof using contradiction. So assume L is an upper bound. Two to the power 2 to the power n basically extends to 0, so we can copy sequence 1 by, so it's like 1 by x tends to infinity, right? Which is basically equal to n, which is also tending towards it. So we can take a subsequence of 1 by x, which is 1, 2, 3, 4. So it's enough to show 2 power n is unbounded. If you assume L is an upper bound, therefore there will be a, like, for all I inside n, the natural number set, 2 power I will be less than L. But from, so if we take log both sides, log 2 to be specific, so log 2 to the base, log L to the base 2 is greater than I, but it's like if we take capital N to be log L to the base 2, so log L to the base 2 is a natural number, is a real number, right? Let's call it like alpha. Therefore, alpha is real. And from Archimedes' theorem, there exists a natural number n such that alpha n is equal to twice alpha, right? So n is inside naturals. So there is a natural number n that is actually larger than alpha and is equal to twice alpha. Therefore, we will pick that I. So let I equals to n. Therefore, 2 to the power twice alpha is, you can say like twice alpha is greater than log L base 2. That implies 2 to the power twice alpha is greater than L. That implies 2 to the power n is greater than L. Which is a contradiction since we thought or we assumed nothing is larger than L. of the form 2 power n, but we got a contradiction. Therefore, 2 power n is unbounded, and so is 2 power 1 by x, so it can't be convergent. Okay, let's introduce a new concept. So, concept of closed and open sets. So, intervals can be closed and open, right? Like if I say -1, 3 is a closed interval. Similarly, -1 to open is an open interval. What about something like -∞, 0? So this is also an open interval. So what is a closed and open actually means? So in terms of sequences, it actually has a pretty what can I say, like a pretty tight definition. Not exactly intuitive one. So we say a set. A set S, which is a subset of real numbers, is open in R if for all x in S there exists epsilon positive, such that x minus epsilon and x plus epsilon in this interval is inside S. So you see what the definition says. So let's imagine this is the number line, and this is -1, this is 3. So, okay, 3. Let's say 2 first. So the open interval -1 to actually doesn't contain the number -1 and +2. but anything in between, right? If we take any number, say suppose x, then we will have a interval, a small interval around x, which will have numbers. I mean, whenever you have two numbers, two real numbers, suppose x and 2, one will be smaller than the other. So there are few basic terms that make up real numbers. One of them is total order, or it's a strong form of partial order. So that says between any two real numbers, x and y, only three things can happen: x is equal to y, x is less than y, or x is greater than y. So assuming one of these have to happen, if x is equal to or x is greater than y, these two will imply it's outside the interval, open -1. Only this thing can happen. When x is less than y, then y minus x is actually a positive real number. So we can take that to be r, epsilon. Or something a bit smaller than that, maybe y minus x by 2. And then we have x plus epsilon and x minus epsilon totally inside x, right? Or here in this case, open -1, 2. And it's just 2 for all x, not just it's 2. So you can see we can always have such epsilon. So epsilon is basically minimum of 2 minus x and x plus 1 by 2. If we take this epsilon, then we are always guaranteed to get an interval, a ball. These small open intervals are called balls. We will get a small ball around x, which will be totally continuous. So that's why you can show it S is open from this definition. Now, is this same thing true for this interval -1 to 3 closed? -1 to 3 closed interval doesn't actually contain, so if we take x equals to -1, we are stuck now because -1 -1 plus 1 is 0. It's no longer a positive real number that we can take epsilon to be equal to. So it's x is exactly on the boundary. We can't take anything to the left, so we can't have a ball, a symmetric ball around x, which would be totally inside S. So this set can't be a closed, an open set in S. Anything that is not, it's not the same. So yeah, this is not a open set as now we can see. First is actually closed. We have to look at the second property. So set is closed if if there are numbers in the set which says that every ball in that around that number has numbers inside that set and numbers outside that set. The definition: a set S or a subset S. Subset S of real numbers is closed if only there exists X in S such that for all epsilon greater than 0, X minus epsilon and X plus epsilon so there exists Y and Z inside this X plus epsilon and Y plus X minus epsilon interval such that Y in not inside S and Z inside S. So it's easy to see if we take 3 or minus 1 as x, then we will be able to pick any epsilon small enough. I mean, let's pick epsilon to be 1. So then we have the interval 2, 4. And then we can take y to be 3.5 and z to be 2.5. So z is inside our set, closed minus 1, 3, our interval, but y isn't. So this is the existence of a single such boundary point actually proves this to be a closed set. Okay, now some properties. In real numbers, a set is closed if and only if its complement is open. So the complement of a closed set is open and the complement of an open set is closed. So you have minus 1, 3, sorry, minus 1, 2, you have this set. This is an open set. Therefore, it's complement. So R without minus 1, 2, which can be written as minus infinity to minus 1 closed, union 2 to infinity. So this set is a closed set. So in terms of sequence, if you see a sequence is, so if you have an open set S and if the terms of the sequence are in that set S, then the limit will have to be inside that set if it's closed. But this is not exactly true for open sets. So for all convergent sequence in a closed set, limit xn equals to inside S. So the limit of a convergent sequence is inside a closed set, but no, this is not the case for open sets. This is one of the identifying properties of a closed and open set. For example, if you take the sequence 1 by n, starting from n equals to 1. So let xn is equal to 1 by n. And you take s to be equal to the set 0 to then this is an open set, right? But the sequence, all the elements of the sequence 1 by n are inside this set. Yes. N may be how much larger you may think of. 1 by n is always inside the open interval 0 to. But the limit, which as you can see is 0, the sequence is convergent, the limit is 0. But 0 is not inside this, right? So the sequence, terms of the sequence are inside the set, but the limit is not inside the set. This only happens when the set is open. Hence, the set is open. Now, an exercise. Is the set of rational numbers closed or open? So the set of rational numbers is Q, which contains all the numbers of the form P by Q, where P and Q are integers, and Q is not equal to 0. This is a subset of R. So we can talk about openness and closeness, since up till now we've only defined what openness and closeness is in subsets of R. So try to think about it for a few minutes. We'll be back in 5 minutes. Okay, so did you think about it? First, let's try to see why.
Closed.
Sorry. Oh, you said it's closed, right? Okay. So let's see if it's closed. So first, let's see why this is not open. So if you think of any rational number 1 by 2, say suppose. So there are infinitely many real numbers exactly around half. Like how small a ball you might consider. There would always be real numbers that are, irrational numbers around half in any ball you get. So that will, so for all, so we have to show to prove Q is not open. We need to show for all epsilon positive. No, first for all x in Q, there exists epsilon that doesn't exist. Okay, so I have to show for all epsilon. So this has to be there exists Q in x in Q such that for all epsilon positive, we have we have y inside x minus epsilon, x plus epsilon, such that y not inside Q. So take any rational number to start with. So let x be x equals to 0, since any one of the rationals will suffice. So let's take x equals to 0. Now, for all epsilon, so we can take any general epsilon. So our interval is minus epsilon to plus epsilon. This is our interval I, or the ball. Now we have to find y in terms of epsilon, says that it's not in rationals, but is inside this ball. So to quickly get hold of such a rational numbers, let's assume so let's take a rational smaller than rho. So any rational number is of the form p naught by q naught, right? So if p naught by q naught is less than epsilon, then p naught is less than. We might as well just take it 1 by n. That will make our lives easier. 1 by n. So take m equals to 1 by epsilon plus 1. So therefore 1 by m is now strictly less than epsilon. And minus epsilon is strictly less than 1 by m. Right. Okay. Now, now to get the irrational number, let's fall back on surds. The square root of 2 is around something 1.414. So, by Archimedes' principle, there exists integer n in naturals such that n is n times root n is equal to is greater than any real number. So, or we can say it's similarly less than any real number. Just a minute. We want to find a rational number such that this is less than epsilon. This way we can very well take m to be ceiling of root 2 by epsilon, right? So if we take m to be ceiling of root 2 by epsilon, then for this m, 1 by m times root 2 is an irrational number, and 1 by m times root 2 is less than epsilon from the definition of m. So therefore, y equals to root 2 by m is not inside q, but y is inside minus epsilon to plus epsilon. Since it's positive, so it's inside the interval, right? So yeah, so we have proved the first hurdle, that it doesn't follow. So it's not an open set, since there exists numbers which are inside any open ball around 0, but not in rationals. So this is not open. Now we will prove this is not also closed to. So Snehashish, you were saying rationals were a closed set, right? This is not actually the case. Rationals are not closed. Let's see why. So to show it's closed, we can use that theorem that says like a set is closed if and only if its complement is open, and the set is open if and only if its complement is closed. To show Q isn't closed, we will show the complement of Q is not open. Since it's easier to show things are open or not open as compared to closed and not closed. And mind you, these are not mutually exhaustive criteria. So something that is not open doesn't mean it's closed. Something that is not closed doesn't mean it has to be open. So what is a complement? It's difficult to visualize, but Q complement is just the irrationals, the set of irrationals. So this is open. Sorry. So why this is not open? So we can use a very similar technique that using which we showed the rational numbers are not open. Show irrationals are also not open because other than the transcendental numbers, we can easily work with surds. So we just need to show, for example, of an irrational number z, such that any open ball around z will have things in it which are not in irrationals. So for example, you can take z to be root 2 and epsilon is we don't have any control over it, so epsilon is any positive real. And now to pick y, which is a rational, so we will again use Archimedes' theorem. So we can take, so we need 1 by m smaller than root 2 plus epsilon, larger than root 2 minus epsilon. So we can take, so that means m has to be less than 1 by root 2 minus epsilon, and then m has to be more than 1 by root 2 plus epsilon. Here I'm assuming root epsilon is less than root 2. Otherwise, we have to flip the inequalities. So if we take the ceiling on both sides, then so actually root 2 is pretty small, right? So maybe we should work with some larger irrational, like suppose 1, 1, 1, 1, 1, 1. I hope this is not a perfect square. 5 ones, right? Now we sure have enough range for m. So square root of, so 1 by square root of 1, 1, 1, 1, 1 plus epsilon, the ceiling of that thing obviously is much smaller than the ceiling of 1 by root over 1, 1, 1, 1, 1 minus epsilon if we take epsilon large enough, right? So we can pick m from that. Since these two numbers are not consecutive, so therefore 1 by m is a number, a real number that is in between those two limits. So inside the open ball 1 1 1 1 1 square root of 1 1 1 minus epsilon plus 1 1 1 1 plus epsilon. But 1 by m is certainly not inside q complement, since it's of the form p by q, where p is 1 and q is m not equals to 0. Therefore, q complement is not open. Therefore, q is not closed. So the set of rational numbers is a unique kind of set that is neither open nor closed. Okay, so I hope you are, so this was clear, right? Why this is not open, not closed. Okay, now, so next day we will talk about compact sets, which are special kind of closed sets, which are also bounded. And look at what is called the extended real number sequence. Extended set of real numbers. So I will call it a day here. So meet you next week. Bye. Bye and good night.